had a pendulum and went back and forth and back and forth and back and forth 10 times. What do we call that back and forth motion? What do we call that movement? Oscillation. Oscillation. Right. So the pendulum was 1 meter long, and then we took it from an amplitude of 0.4 meters and then an amplitude of 1 meter. Hope, can you please tell me what is amplitude again? The definition for amplitude. No disturbance, displacement. No disturbance. Okay? Alright. Okay, so we were busy looking at the different variables. Alright? And we started with the constant variables. What did we have to keep constant? Now, why do we need to keep things constant? And I use this as an example. At the beginning of the year, I said when we have athletics and we want to determine who is the fastest in the school. Okay? Can I just let boys and girls any age run against each other? No, it won't be fair. Right? Because a boy and a girl have different hormone levels, so their muscles grow differently, so there will be a difference in the way they run. Then a boy in grade 8 and a boy in grade 12 will also be a very different, because in grade 8 your hormones haven't developed yet, so your muscles are not that great. With grade 9, grade 10 you start to develop, you start to get a beard, your voice starts to drop and so there's big developments, and in grade 12 you're not fully developed, but you're almost fully developed. So yeah, you will run fast in grade 12, hopefully, if you don't develop suddenly. Okay? Alright, so if we want to do an experiment, we want to determine something, we have to keep certain things constant. Now what we keep constant here is we kept the length of the pendulum. So, yesterday we said we kept the weight of the pendulum, so we didn't change the weight. We kept the length of the pendulum the same, and the people that conducted the experiment we kept the same. Okay, because we think that people, when he measured the amplitude, that we measured it the same every time from the same spot to the same spot. The person that did our time, if he was wrong, then hopefully he was wrong in both, the same amount of wrongness. Okay, then what did we change? What did we change in our experiment? Huh? He said what? No, you're not laughing for the word amplitude, then something's not like it. You laugh at the word amplitude. Yeah, I know you're not laughing at that. You are in your way. Okay, now what did we change? What did we change in this experiment? From the first experiment to the second one, what did we change? Yeah, the word is just there. So we changed the amplitude. So the amplitude is the independent variable. The independent variable is the thing that we change. Then what was the thing that we measured, Ona? the time. That was the dependent variable. Now in this experiment, the dependent variable, we measured the time, but it's also going to be the frequency. Okay, what we're going to calculate there at the end. It's also going to be the frequency. Alright, now that time there, anyway, was for how many oscillations? That was for 10 oscillations. Now I want to know what is the period. Okay, Zora, what is the definition of a period again? The time taken for one wave, or one pulse or whatever. Okay, so it is a time taken for one time for one wave. I know all these things. Do you know them? If you don't know them, did you make a note of it? While I'm writing, are you writing? Okay. So the time for 10 oscillations was 18.75. 18.75 was for 10 oscillations. So we want to know how much is that for one oscillation. Retabile? You can take out your calculator, but you should be able to do this in your head. Is going to be 1.875, and the second one? No man, in your head. 1.984. Alright, so that was the period, the time for one oscillation. It's almost 2 seconds. 1, 2. Alright, then we want the frequency. Rorisang. What is frequency again? What is frequency? Yes, the number of waves per second. Okay, so you can do this now in 2 ways. You can either say for 10 waves, this was the time. Or you can say for one wave, this was the time. Okay, so I'm going to do for one wave. So I'm going to say the frequency will be for one wave, this was the time. So for one wave, this was the time. Okay, if you calculate that, what is the frequency? 0.53. Okay, and the other one? I just want to know, did everyone check her? So everyone did the calculation on your own, the same one. Sorry, what did you get for the second one? 0.50. Okay, right. Now, are these two values close to one another? Okay, yes it is. Now, we know that our helpers in the experiment was not very accurate, right? There might have been some human error. And remember at the beginning of the year, I told you that in science we have a lot of gray. We make room for human error. You're going to do a lot of experiments, and I'm going to work with your human error in the experiment. So we can say, you know what, that is quite close to one another, the two values, the frequency. So what conclusion can I draw from this experiment? Don't tell me. What conclusion can we draw? Think about what did we change and what did we get. Okay, so as the amplitude increased, as it got bigger, what happened to the frequency?
It? Did it increase? Okay, what did I just say? They are very similar. They're very close to one another. They're almost the same. Yes? So we are going to say, as the amplitude increase, the frequency remains the same. Okay? Or you could have said a change, that's a C. Are you writing this down? A change in amplitude, Kumo, has no effect on the frequency. Okay, now we have mentioned the two variables, the dependent and the independent, we've mentioned. And we've mentioned their relationship. Okay, now relationship is not I like you, you like me, give me flowers. Relationship is how do they relate to one another. As the one increases, the one decreases. As the one increases, the other one increases as well, has no effect. Okay, so we've mentioned the two variables and we've mentioned the relationship. Now this, in a test exam, will count 1 mark. I want, for another mark, I want you to mention the control variables. Okay, so these two will only be the same there if the length of pendulum remains constant. Okay, so you must mention the thing that you keep constant. So I'm going to highlight here. I want you to mention the amplitude and the frequency, so our two variables. I want you to mention as the one increases, the other one remains the same, so their relationship. And then I want you to mention the controlled variable. Now we're going to do another activity. It says there, class activity 2, how does the length of the pendulum influence the frequency or the period of the wave? Okay, so now we already did with a length of 1 meter, and an amplitude an amplitude of 0.4 meters. We did that one there. So I'm not going to do that experiment again. I'm just going to write down my findings. So this one, I'm going to write down there again. So we got that to be 18.75, 1.875, and 0.53. Okay, so in yesterday's experiment, we took a very long pendulum. Now we're going to take one that is a bit shorter. How short exactly? It's going to be 0.5 meters. Okay, where's my helpers? We must have the same helpers because we want to keep the things constant. Alright, now as I said, the length must be 0.5 meters, that is 50 centimeters. Are you ready? Are you ready? Okay. 3, 2, 1, go. And 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It will be fun. It will be fun. Thank you, guys. You can take that off, please. What did you get, Kumo? 1462. 14. Play with it. It will distract me more from my lesson. Okay. So we got our time. Now we need to calculate our period. Pole, how are we going to calculate the period? We did it there at the top. Just wait. Yes? Why do you say over 10? How many oscillations did we count? 10. So that gives you 1.462. And if we determine the frequency, Relo?
0.5 over 1.462.
Why do you say 0.5? 1 over 1.462. One wave took so long. Okay? So if you didn't know that, then make a note for yourself. That one refers to one wave. Okay? You might laugh at her now, but I'm going to laugh at you in a test. What do you get? .68. All right. So that is not close to one another. Okay. There's almost a 10 per second difference. Okay. So, Pukumuso, what relationship do we have between the length of the pendulum and the frequency? Okay, so as the length decreases, what happens to the frequency? It increases. Okay, so you are going to write as the length of pendulum increases or increase, the frequency. Sorry, not the length of pendulum decreases. Sorry, decreases, the frequency increases. Okay, but what must we remember? Don't tell me. Starts with an L. Listen, Eddie. What must we remember when we write a conclusion? What am I looking for that second mark? You can. Who do you want to call? Are you picking up? Okay. Yes, what did we keep constant? Okay, yes, the wave, but the thing I'm looking for here is the amplitude. So the amplitude here is 0.4 and the amplitude here was 0.4. Okay, so if amplitude remains constant. Okay, now you can either write it a long sentence like that, or you can use a relationship phrase. So the word or. What will that be, Khali? If the one becomes smaller, if the one becomes smaller, the other one becomes bigger. They're like opposites. What fancy wording can we use there to describe the relationship? Say again? Almost there. Inversely proportional. Okay, well done. So you can say the length of pendulum is inversely proportional to the frequency. Yes. Yes, but then you're going to write it like this. Length like that. Alright. So an experiment like this you should be able to do on your own. Okay, you should be able to see which one is the dependent, which one is the independent, what is the control variables, write a conclusion. Chuck. But you did that a lot last year with experiments in natural sciences? Yes. Get what? That? Table. If I ask it in a experiment type of way, I might give you the table. I might fill in almost everything except for one thing. Okay. There will be what? No one? In a test, no. Alright. Then we're going to look at the next concept. There's a transverse wave. So we had a transverse pulse. Now we're going to go to a transverse wave. What does that D stand for there, Cloney? Definition. Yes, what does that D stand for? Definition. What do you know about definitions in the science class? Speed test. And word for word. Okay, so what is a transverse wave? A wave in which the particles of the medium vibrate at right angles, or you can say perpendicular to the direction of motion of the wave. Now that which is in brackets afterwards is not part of the definition. A transverse wave is a succession of transverse pulses. So it just means a pulse is one, doop doop, and a transverse wave is if it goes on and on and on and on and on. So pulse is one, a wave is lots. Then I tell you there, water, light, radio, TV, and cell phone waves are all examples of transverse waves. There you can see someone has a rope, and he's making this rope go up and down like that. The wave moves to the front, but the rope goes up and down like this. Okay, right. Then we are now going to start to do calculations. Okay, for calculations we need formulas. The first calculation that we're going to do is we're going to determine the speed of waves. How fast do waves travel? Okay, why do we want to do that? We want to get to a place where we can determine if we see a star in the universe, we want to know if that star explodes. How long after the stars explode will it take for us to notice that? Okay, you know the closest star is how many light years away from Earth? 4 light years. So it means
goes out, so it's finished burning or whatever happens to it, it will take 4 years for us to notice that. Only after 4 years the sun will go out. Okay, that's crazy. Yeah.
Is that star already dead? Sorry,
Already dead. Alright. So that is what we're moving towards. We want to actually calculate things in real life, but we're going to practice it first in science class. First, the definition of the speed of waves. Right, I see you later on again today. Yes? If you want to, you can leave your books in my class.